much light is being absorbed by the compound, and depending on the light you shine onto the compound, different things will happen. Okay? So for our infrared, what will happen is it will absorb the infrared, and in that region, the bonds will start moving and shaking and things like that. Okay? And a good thing about all of the transspectroscopy is it doesn't destroy the sample. It's going to just either let the light pass through, or it's going to absorb it, but it won't break apart into pieces. So like I mentioned, so for IR, so our molecules will absorb the energy, and the bonds between the atoms will either start to stretch, bend, or rotate. And some of the things that happen, like Alex will dance for you, is symmetric stretching. Right? Antisymmetric or asymmetric. In-plane bending. Yep. And out-of-plane bending. Alright, so these are some of the things that will happen, and based on how much energy is required, you'll see different strengths of signals. Okay? And the region between 600 and 1400 is called the fingerprint region, and this is because there will be an overlay of all different types of peaks, and you can't identify each one. It's just be like a huge mess. And just like your fingerprints, you can't really assign each ring. That's why it's called fingerprint. Okay, so it's unique to every compound, but you can't really tell anything from it. Okay. And so the handout that Dr. Nichols sent you said to look at the bonds as springs. Okay. So basically, all we're trying to do in IR is figure out which frequency each function will try to come in at. Okay? So one of the rules that you should pay attention to is heavier atoms decrease the frequency of vibration. Okay? So if you think about that as a spring, like the heavier rock you put in the spring, if you flick it, it will flick much easier than something that's light, which is opposite if you think about it, but like if you try the experiment yourself, you'll know that if you put a heavier end on one side of the spring, it will move a lot more and a lot faster. Okay? And that said, if you have a stronger bond, like a triple bond or a double bond, it will require more energy because now it's more stiff and it's shorter. So if you want to try to flick a spring that's really strong, then you will need more energy to make it vibrate. Okay? So if it's stronger, then the frequency will become higher, and if you have heavier atoms,
you said heavier atoms, what?
Low. Vibration will be lower. Okay, so and another thing that goes into that, we talked about triple bonds and double bonds. So triple bonds are SP, so SP will have the highest frequencies and things like that. Okay, so Akriti, I would like you to answer the trend that you expect here. Which one will have the highest frequency? I'm asking her. Is it, so which one's going to have the highest frequency? Triple bond, double bond, or single? Okay, and then? Good. I want you to answer the second one. Put them in order, from highest to lowest. Bromine. Is bromine the heaviest in that series? Everyone agree? Okay, so for this one, we're looking at the trend of the mass. Right? So iodine has the highest mass, therefore it has the highest frequency. And then, figured out? So the last one, we didn't really talk about this one, but I want you to guess. It's going to still follow this kind of order. So what I talked about was triple bond, double bond, single bond. But you have this hydrogen that's next to a triple bond, right? So think of your triple bond already being locked in. And so this one is not as flexible because this one's already locked in. Understand? So that's why this will also be the highest frequency and higher, lower, and then lowest. Yes?
Triple, double, single. guys need to give a big thank you to Sonia. So, thank you. She's so nice.
Alright, so as this picture shows you, who can tell me what CE is after CH? It's a heavier isotope, right? It's called deuterium. And what?
He's just talking.
Okay. So what happened when I went from hydrogen to deuterium?
You got heavier.
It got heavier, and what happened to the frequency?
It decreased.
Right, so that's the trend that they're showing you. And what's happening here? What are they trying to show you here?
The more bonds,
Higher the frequency. We're going from single to double to triple. So what happened to the frequency?
It's increasing.
It's increasing, and it's the same thing with nitrogen and oxygen. E is the isotope of hydrogen, so it's double the mass. Okay, so I only talked about fingerprint vision. So the region that we usually focus on is called the function group. Okay, so this is where all the function groups would come in, and you can identify, like you can actually pick out peaks and label them. But in fingerprint region, they're all overlapped. It's a mess, so you can't really tell you. So your spectra, as you've noticed from your worksheets, the x-axis is called the rate number, and that's 1 over frequency. It's just easier to work with. And you have percent transmittance on the y-axis, so that's just going to tell you how much light is being let through from the compound. Okay. And so the strength of the peak depends on the dipole moment of the function group. So you have CO. Is that going to have a high dipole moment or low? High, because you have an electronegative oxygen and you have a carbon, right? So those kind of things will have a huge peak. So if you look in your spectra, CO bonds will come in, C double bond O come in at around 1650, so that will almost touch the baseline. Okay, so our spectra usually go this way, which is not what we're really used to. It's always going up. But it starts from the top and comes to the bottom. Okay, and things like C double bond C will not have much of a dipole bonded to the same atom, right? So those will have really small peaks. So there are strong peaks, medium peaks, and small peaks, and that will depend on the dipole moments of your functional groups. And so the types of information you can get from IR is obviously the functional groups, and just like your NMR, you can also identify the purity based on it. And so the one thing that it can't do is tell you the order of functional groups. Okay? So if I have a double bond and it's showing me a C double bond, the peak in my IR, I don't know if it's at the end, in the middle, or where in my molecule. It'll just tell me that I have that. Okay? So it's useful, but it doesn't give you the full picture. So with that said, let's go on to question 1 and 2.
Can I ask a question?
Of your worksheet.
It does tell you for the IR. It does tell you the just the dipole moments, but not the order.
It doesn't tell you the dipole moments. I'm saying, okay, the dipole moments are important to see how strong the system is, okay? So you see this peak is really small, and this one is longer. So the dipole moment here is greater than 2.
Okay.
It's not saying anything about the dipole moment as the overall molecule.
Okay.
You said the IR doesn't, it tells us if you have a triple bond or a double bond, but it doesn't tell us where it is.
Yes.
Is there a way to figure that out?
NMR.
Okay.
NMR.
NMR? Okay.
Promise we're going to get there.
Alright, so question number 1. A tells you to identify every single CH stretch in the iron spectrum. Alright, so where do CH stretches come in?
It's right there on the left-hand side.
Give me a number, guys.
Between 300.
Around 3,000, right? Do I see 2 different peaks in here?
Yes.
Why do I have 2 different peaks?
Because you have bonds. Your bonds are different.
Look at the molecule. Okay. What
You
else?
said, why do you have 2 different peaks?
Yes. So
'Cause
the
different.
spectra, the guideline sheet that Dr. Nichols gave you, it shows 2 peaks, right? And remember, Alex demonstrated that there are different things that our bonds are doing, right? So one of them will have more energy than the other ones. So not all of them have different peaks, but CH stretches have 2 peaks. Okay, one in the higher frequency and one in the lower frequency. So what happened when we go to our hexene? What's new?
Small bond.
We have a small peak above 3,000. What else? There's nothing else down below. I see nothing here and
On the right side.
something here. So again, your alkene CH structures also has a lower frequency. Okay? Does my hexene also have alkane peaks? If so, why?
You got
My
one.
alkene, so I have hexene at the bottom.
You got one in the middle. Will still be a hexane. You still got the one hexane in the middle,
Right, so
or somewhere in there. Maybe not the.
So one hexene looks like this. This part of the molecule is the alkene. All of this is still alkane. Right? So you should expect to see those. And so what happened when we went to alkyne?
Again, the same two areas. You got the stronger.
Right, so basically
Frequency increased.
yeah, the frequency is increasing, right? So when you're labeling these, make sure that you identify CH stretch and said that it's for an alkane, because CH stretch, there's alkane, alkene, alkyne. So for this one, you're going to say CH stretch alkane, CH stretch alkane. Here you'll have one CH stretch for alkene, one stretch for alkane, and then alkane. Should I have any alkene peaks in my hex sign? No. It's just triple bond.
Wait, could you say last time you were saying alkene stretch and alkane stretch up to a second?
Yeah, so this here is our alkene. This is alkane. Alkane. Alkene. Right? And that's based on the guidelines where each frequency would come in.
And you said, what did you say about the hex sign?
Next sign, you'll have CH3 alkyne, and then CH alkane, alkane, alkyne.
How would you say, what's the last part?
Alkyne, alkane, alkane, alkyne.
Well, why do you have two alkyne? I don't.
Right? It's not based on the number of hydrogens. Remember. It's based on what the bonds will be.
Okay.
I don't know.
Kind of
She threw me off.
the,
Yeah, well, she said something over here.
we don't know what that
I keep getting mixed up with alkene, alkyne. I know alkane. A-N-E. Yeah, I understand that one.
Look at your peak and where each stretch comes